That's pretty much it for the demonstration. It's been an hour already, so let's move quickly to Q&A. Hopefully this was clear enough, and the modeling part was interesting to you. Let's open up the floor.
Thank you very much, Hervé. If anyone has questions, please feel free to post them in the chat. You can also ask to take the floor with your microphone, and just let me know in the chat, and we'll make room for you. So Hervé, what are the main difference between the test error at 53% and the 8%? This was based on the model. Well, I guess it means was based on the model being used.
Yeah, no, so that's a good question, and thanks for asking that, because I've been pretty quick around this. Basically, in the first instance, what I have done is used what I call correctly split train and validation sets. So as I said, basically in this slide here, the way to split train and validation is to keep the time dimension in the data, the time structure. So let's say X here is time dependent. So on the left it happens in the past, on the right it happens in the future. So if you split randomly, meaning that you take the random forest package as it is already coded, and you just dump the data in it, what it's going to do is going to take out randomly some data to use it as validation. So validation is a way to assess how the model performs on unseen data. The problem is in our structure here we have a time dimension. So this is important because in the future I'm going to have always this time dimension in my forecast. So I'm always going to try and predict what's going to happen in the future. I'm never going to try and predict what's happened in the past. So it is important because if you don't do it this way and you take the random forest as it is, it's going to do it like this. It's going to take the time series, you feed it, and it's going to randomly drop at points. But there is no much value in doing that, because your model is then learning how to fill gaps or how to bridge the difference between 2 points. It's never learning what should happen afterwards. And this is exactly what's happening here in my training. Here, the first time I've trained, here I've constructed a train set and a validation set. So here my train set is the sequence from 1 to it's easier to do it this way. This is my basically my training set. So from index number 1 to index number whatever the length of that stuff is. And my my validation set here is the rest, is starting at 1255. So the index 1255 to the end of the data set. So it's keeping the chronology. I'm taking the first part to train and the second part to forecast, and that's how it's going to be in real life. So you need to keep that structure. Here, if I get rid of this, I just say to the random forest package, just use 2 data sets, but rather than doing it the way I've asked you to do it by indices that are consecutive, you just do it randomly. And when it's doing it randomly, it's basically doing this, getting rid of points randomly on the data set. Then your out of sample error looks really good, but you're not learning what you're meant to learn. You're just learning to fill the gaps, and that's dramatically wrong in the sense that your model is as good as any models to predict the past, but it's not good at predicting the future.
Thank you, Hervé. I have 3 questions coming up in the chat. The first question from DL. Basically, DL would like to join the competition, but he says he only codes in Python. He's asking if he's forced to code in R or if he can just code in Python and show us the results.
So the latter is not possible. You cannot code in Python locally and then drop it in Alphien, because all the work that is done during competitions is done on our server, on Alphien server, and the reason is when you do a competition on Alphien, you are building a strategy, and this strategy has the potential to be distributed to asset managers in the future. To do this, we need to make sure that first of all you fully own the code that you have written, but also that it remains secured and private to you and to Alphien. So this is the reason why everything is done locally on Alphien. So you cannot just work locally and then drop the results on the platform. You won't be able to get the input data either, because the building blocks are proprietary to Alphien. So that's going to be difficult. On the second part, on the Python part, at the moment it's not available on the platform. That's it for now. It's R. R is not much different from Python. There are dissimilarities, of course, and when we're used to using one, it's a bit of an effort to move from one to another, but it's not insurmountable, and people usually manage to do it. So what you can do for now is just try to follow the basic examples. Everything that I write here, I make it available to users. So you just copy the code directly from what I've done and just try to improve it at the margin. You'll see that if it's in R in Python, it's not much difference because the heavy lifting has already been done for you. So you just need to tweak and fine tune and then mix things together.
Thank you for your answer, Hervé. I would also add that, you know, if you need any help with your code, most people at Alphien can write both R and Python. So you can always use the live help if you have a problem, and we will help you translate your code. Next question. It's from Hassan is the next one. How do you ensure that the model is not overfitting?
Well, that's a good question, Hassan. Thank you. And my preconization is to always use a training, validation, and test approach. So in what I've showed, basically, I've trained on 70% of the data I split initially. So let's go back to it. Split data here. It's getting me two data sets. One is called train, one is called test. So the test set, by definition, is always something that I will never look at. I will never glance at the data that's in there. It's going to be for prediction only, just to make sure that what I've done is good on unseen data. So I'm just leaving it aside. So when I'm doing split here, I'm only using the train set. Now, when I'm training, indeed, the good question is, how do I make sure that when I'm training, I know at which point I'm overfitting or not? And the answer to that is, and I'm going to show it on XGBoost in a second, is I use a validation set. So I drop out 30% of the training set. And as we just explained, it has to be the most recent part of the data set. And then when we do the training, and we're going to do it here with this XGBoost, I'm just going to structure it correctly this time so that it doesn't look too good. Too good to be true. If I just training like this here, during the training, it's telling me every 100 epoch, it's telling me this is your error on the data you've seen. This is 2% error. But on the data you've decided not to see, which is a validation, your model is random. And then it's going down. And then it keeps on going down. And typically what happens when you overfit is that you see this error on the left. So here it's going very quickly, but if I just change this to make it learn rather slowly, so this is going to learn much more slowly. So here, it goes only from 2 to 1% error. Not only it's learning more slowly here, but here it's not learning anything on my validation set. Actually, it's not learning. It's not quick enough. That's the learning rate. So how much learning do I inject in my model, basically? So Here you see that it's going to drop probably to 1.8%, but here at the same time it's learning something, because first it was 53% error, now it's dropping a bit. Typically, when you run that for a long time and the model starts overfitting, you will see divergence. Your train error, so the error on which you are showing, you are training, you're seeing the data, is going to keep decreasing, but the error on unseen data is going to start to diverge. It's going to start going up. And that's typically what overfitting is. Overfitting is not having a much smaller results on the data you've seen that the data you haven't seen. This structurally will always be the case. The overfitting part happens when you start learning, so you go down, and then you start diverging. So now it's going up again. Or it's learning back. But and typically, if I draw this, you will have a curve here that is going to drop and then go back up. And the time when it's going back up, it's when it starts overfitting, basically. So what you want to do is cross-validate, just like we're doing here, and decide to stop here, for example, at 200 epoch, which is basically what I've done here. I've stopped at 200 epoch because I know that after 200 epoch, nothing happens.
Thank you very much for your answer. My next question is from Hamza. He's asking about cross-correlation as a feature, and how can cross-correlation be useful and be incorporated in a training set?
Well, it can be indeed. Thanks for the question, Hamza. As we've said here, this is what I've listed under exogenous transformation, and you can add cross correlations. So what you need to do is to build every pair of cross correlation in the data set and add it to your initial feed data here. Yeah, let me just write it. Feed data, and you just add it as new features, basically. So here you'll have correlations between series A, B, C, and D. Just remember that initially we had 22 series, and if you want to have, you'll add 231 new series by doing just cross correlations. You can also do other transformation than cross correlations. You can use other dissimilarities, cross correlations, or linear similarities or dissimilarities measured, but you can try and have dynamic time warping, for example, which is non-linear dissimilarity measures. So hopefully that answers your question. Basically, you add much more features to a data set. One important point maybe I need to make here is a lot of there is this concept in the literature that's called the curse of dimensionality, and empirically it doesn't apply, especially not on tree-based models. Tree-based models, they work in very large data sets. They like to have very numerous features, and you can see that when we train with 800 features, then we can basically reproduce the model down to 10 features and have somewhat the same results. This means that the model is not uncomfortable with having too many features. It's just very capable of ignoring what's not helpful. It's just taking more computation because it's trying every combination, but it's just a computation problem rather than a performance problem.
Thank you for your answer. My next question is from Anthony. Once a model goes into production, how often is it retrained? For example, is it annually?
Yeah, that's a very good question, Anthony, and I think that's linked to Greg's question also after that, which is asking to how do we include this sort of modeling inside our payout on the platform, and that's the question that we would like to answer much more deeply than just in a few minutes. I would say I will give you a short answer, but we'll probably need to schedule a webinar to cover in depth this topic going forward. But short answer is basically you can choose the frequency at which you need to retrain the data. So if you take this XGBoost, for example, you've seen that I had a part where I was just testing the data, cross-validating the model to basically pick up, this is the gist, to pick up what are the correct parameters. So I haven't gone through details here, but there is many ways you can combine these parameters. And then once I had the correct parameters, I know that my model is going to use them. So this is my actual training, and then I'm doing a prediction. So this training here can indeed happen many times. My advice would be to include this training inside your payout, but only to trigger it every, I don't know, as Anthony said, 3 months, every 1 year, every 2 years. It depends on the objective of your model. If your model is very high frequency modeling, you probably want to retrain it more often than every year. But if it's as it's the case here with a 3 month trend type of modeling, you want to retrain maybe once a year. It should be enough. One important point about retraining is don't lose what has already been done. I mean, when you're learning something, you don't want to retrain from scratch every time. Well, at least that's my advice. It's like when you're doing math, you're not totally forgetting about geometry when you're going to do analysis. It doesn't make sense to relearn everything from scratch. The most powerful machine learning models at the moment and state of the art in vision, text, or anything where it's successful is using transfer learning. It means it's using something that is already pre-trained and improves it or make it custom to a new problem. And I think that should be the case also from your modeling. When you decide to retrain your model, don't lose what you have already trained it to do in the past. So train it at the margin, not retrain it from scratch, if that makes sense. Hopefully that's clear enough.
Thank you very much for your answer. I guess you answered both Anthony and Gregory, so I will move to KP's question. How do you interpret the feature when the number of dimensions is reduced in principal component analysis?
So indeed, PCA is going to reduce dimensions based on variance. So it's going to project all dimensions into a reduced set of dimensions. As the question implies, it's quite difficult to understand these. Usually, you need to have some sort of insight or expertise in the subject you are looking at to be able to make sense of what's being projected. However, often it looks like you're post-rationalizing something, so there is a result and you're trying to make the explanation fit the results you're getting. So unfortunately, I don't have a straight answer for you at this stage, but interpretation is indeed somewhat of an issue, or actually raises some questions and some unanswered some problems in this field. I don't know if you can interpret the features. What you can do though is you can use PCA and then throw it into a random forest, for example, or an XGBoost, and then decide to select the components, which components to use through the importance of the model that we've seen before, like this. So that basically in this chart here, you'll have, I don't know, component number 2 and number 3 as the two first features, and then you can try to build your models based on these features. What do they mean semantically is much more difficult, and I'm not sure there is a straight answer to that.
Thank you very much for your answer. I believe this was the last question. I will leave maybe a couple of seconds for anyone who wants to add another question to the list. Okay, there's a follow-up question from Yuski. So the output of our payout are simply the generated predictions 1, 0, 1.
No. At the moment, in this very model, the output is either 1 or 0, or -1. Sorry, you're either long or short. You're always in the market. So let me find it back. Here we go. This is it. So you either, so that's the purple line. It reads 0 here because we have changed the scale so that you can see everything. But basically, you're either -1 here or you're 1 here. Okay, so you're always either short or long. You can try to derive the multi-label. Yeah, no, -1 and 1. There is no 0. See, there is no midpoint here. So that's why when we run our, so here you're training, so that's pretty good because you see what I've used here on this graph for training, and what I've used is only this, and that's the reason why I could use it for training, is because I decide that this is my limit, and that's all of this information is already available to me in the way I train, and my predictions is only looking right from this. This is my future. So this is why I could label it this way. It's because for training, I know that all of this is available to me. And if I go back to my strategy, where is it? Here. Yeah, that's my strategy. Here you can see I've stopped my training here, and most of the time it was a downtrend. It was a massive downtrend actually. From 2010 to 2016, it was short all the time. But yet, my model was able here to pick up that I need to be most of the time long, which I think is quite good for a model that has only seen, or almost only seen 66% of the time that you need to be short. Here it's telling you no, you need to be long pretty much all the time, and here or actually go short. So it's pretty good in terms of actually explaining the model and doing something interesting. And about the snippets, I haven't answered that question, but yeah, we can publish that in the next few weeks for you, Greg, just to show you an example. But as I said, I would rather have a webinar to cover the subject because it's pretty tricky to get right.
All right. Thank you very much. I guess this was the last questions we could take. We are reaching the end of the meeting. I want to thank Hervé for your presentation and for taking the time to answering the questions. And I want to thank all our participants, both for attending and for asking very relevant questions. We hope to see you soon in our next webinars and on the platform, and we are always available in chat and in forum to answer any of your questions. Thank you very much, everybody. Have a good day, and we'll see you around.
Thanks, everyone. Have a good day.
Okay.